So as Asher mentioned, I'm working on distribution-free uncertainty quantification with Aditya Ramdas in the stats department. Today we're going to be talking about distribution-free calibration, which is one form of uncertainty quantification, which is particularly relevant for ML classification problems. So this is the outline of the talk. I'll first talk about what is the definition of calibration, why it is relevant for you, and why you should care about it. And this first part is going to be mostly in the binary calibration setting, where I'm just kind of motivating the basic definition, which makes most sense in the binary classification setting. And then the next part of the talk, we're actually going into the meat of the main paper of the talk, where we go from binary calibration to multi-class calibration. And then the third part will be how do we achieve these notions of multi-class calibration. So the second part, I'll define various notions of multi-class calibration. And in the third part, we'll actually go into how these are achieved. And finally, we'll look at some experiments with deep learning data sets where our model outperforms other setups for calibration. The main paper for this talk is going to be this recent paper, which is going to be presented at ICLR this May. And that's top label calibration and multi-class to binary reductions. So as I previewed, basically the main focus of this paper is going from multi-class to binary. And the other two papers, which are two prior papers, the main focus is on binary calibration itself and some theoretical guarantees. But for today, we're going to be focusing mostly on multi-class and more algorithmic results rather than theory. Okay, so what is calibration and why do I care about it? We all know that a number of ML and statistics applications rely on probabilistic predictions. So some examples which you may not have seen before is the influential discrete choice framework by McFadden, which received the Nobel in economics. And here they're trying to basically model probabilistic choices of people among various discrete choices, like do you take the bus to come to CMU, do you drive to CMU, do you walk? If you have options of doing all three, what probabilities do you take them with? And they've shown that this probabilistic modeling is actually useful to decide where to invest your funds in terms of like developing various modes of transport and other things. Another natural application is medicine. And in this paper, Spiegel-Harter argues that it's essential to have accurate and useful probabilistic assessments of future events, especially if you're looking for detecting the probability of various diseases or categorizing patient risk. Like if you have a limited set of beds, which patients do you admit and which you don't? And again, it's argued particularly that probabilistic prediction is very useful. And finally, an example that's closer to home for everyone, which is especially in Pittsburgh, which is predicting the probability of rain. So if you look at your weather app and it says 70% chance, what does that mean? And that'll be a motivating example that I'll go a bit deeper into. So how do you interpret rain forecasts? So I pulled up weather.com's forecast today morning. And as of today morning, it was a 70% chance of rain. And what does that mean? Suppose it rains tomorrow, then you'll be like, okay, great. I'm happy I saw this 70% chance and it actually rained. But what if it does not rain? Well, you're probably happy, but at the same time, you're like, I made sure to carry my umbrella and I was, prepared for rain. I made sure I got my rain shoes. I didn't get my good shoes out or whatever, and it did not rain. So should I be annoyed with weather.com? Well, so in this case, weather.com has some kind of plausible deniability because they did say that with 30% chance it was not actually going to rain, and they'll be like, okay, it did not rain, and we were not like saying that it's going to rain with 100% chance. So how do you actually like judge this? And you can't judge it on a day-to-day basis, but what you can do is judge it on a long-term basis. So suppose on many, many days of the year, so suppose this is the predictions of rain for 1 year, and you predict 0.7 or 70% on a bunch of days. Then suppose on the first day, which is like tomorrow, it actually does not rain. Okay, but then later on, you see that it did rain on some of the days. So what you can do is put all of these predictions together and say that on all the days when you predicted or weather.com predicted that the chance of rain was 70%, did it actually rain on 70% of those days or 0.7 times n of those days? And if this is true for the various predictions made by weather.com, then it would be, we could say that the probabilities are calibrated. Or in other words, there's a statistical consistency between what is predicted and what the empirical frequencies of labels or of whether it rained or not is. And on the next slide, I'll go into the ML setting where these probabilities will be predicted label probabilities by your classifier, and the zeros and ones will be your annotated class. So here we'll be looking, so in the case of rain, you can just look outside your window and you know whether it rained or not. But here, when we say zero, it's the label annotated by some annotator who we assume would be the ground truth. Okay, so let's get into the definition of calibration. But before that, like do you actually have this problem in ML models? And that's, and you actually do. So ML models are typically miscalibrated. So in this example, we have a knife-based classifier, which is highly accurate. And we plot on this simple chart what happens when the probabilistic prediction for the class y equals 1 is a particular value. So let's say it's roughly between 0.8 and 0.9, which is basically this point. Then even though this classifier is highly accurate, it turns out that the observed probability of y equals 1 is not that high. It's just about 0.5. So in some sense, for all of these predictions, the model is highly overconfident. Ideally, what you want is that all of these points are on this line, which is the perfect calibration line. And this is not what we see in practice. And this actually occurs for a bunch of models, not just knife-based. This is just one example from a popular paper, but it occurs all the time for logistic regression and random forests. And recently, a lot of deep learning folks have been interested in figuring out if you can calibrate deep nets, which tend to be overconfident. Okay, so let's now define formally what calibration is. And informally, I have it on the title that if predicted probabilities are consistent with empirical frequencies of labels, then the model is calibrated. So in binary classification, suppose you have labels y in 0 and 1, then a predictor which takes a feature x and gives you a score in 0, 1. So it doesn't just give you a label, but actually gives you a score. Then this predictor is said to be calibrated if when a particular score hx is reported, then on all those instances, the probability of y equals 1 is also hx. So in some sense, you condition on what you report, and then you check if on the instances where this particular report was made, was the label distribution consistent. And in this case, there's just two labels. So you just look at the probability of y equals 1. Okay. I'll wait for a few seconds if there's any question, because this is kind of fundamental to the remaining talk. Okay.
You have a question in the chat. I don't know if you want to answer that or not.
It's about the previous slide. I can ask it again.
Yeah, I can read it. I can see the question. Yeah, so classically, overfitted is a question of how well you go from calibration to test or validation to test data. So if you're doing very well on validation data in terms of accuracy or something like that, and then you don't do well on test data, then you would be overfitted. So calibration does indicate that you've kind of overfitted in a certain sense because you're overconfident, but it's not necessarily the case. So in particular, you could be miscalibrated even on your validation data. So you would have or your training data. So you would have evidence that you're actually miscalibrated. Unlike accuracy, where you would see like 100%, but it's actually like 80%.
I see. Thank you.
Okay. Yeah, thanks for the question. So some of you may think that, well, you're not actually going to get exact equality because you're in finite samples and you're not dealing with asymptotics. And in that case, we're going to be replacing it with an approximate equality sign, which is formalized later in the talk, but informally, with high probability, you want the LHS and the RHS to be epsilon close for some small number. But we'll go into the formal details. But if somebody is like already thinking about how you can actually achieve this, theoretically, then you're right. You have to have an approximation between the LHS and the RHS in practice. Okay, so this is one important thing that you have to just remember, that throughout this talk, I'll be using little h or boldface h to refer to a calibrated predictor. And sometimes I'll be having miscalibrated predictors, and they'll be referred with a different letter, which I'll tell you now. So in general, I mentioned that ML classifiers are not calibrated, but they can be post-hoc calibrated. And what post-hoc calibration means is that you fix your model on some training, you fix a pre-learned model on some training data. Now you don't change that model, but you sort of calibrate it. You learn a wrapper around it, and you move. So I'll go into the details, but basically you're doing something on top of an existing model that has been learned on training data. So let's say you have a miscalibrated predictor G, like the one I mentioned a few slides back for the adult data set. And throughout this talk, I'll be using G to refer to a miscalibrated predictor. And this can be any model, absolutely any model learned on training data. It could be a deep net model, it could be a simple naive-based classifier, it could be anything, as long as it gives you scores in the interval 0,1. And now the question is, if you want to calibrate this, what do you do? So what you would need is some additional held out calibration data, which I refer to as D. And there is n calibration data points. And I want to put this into this black box and get a calibrated predictor on the right. So as I had mentioned earlier, this calibrated predictor also is always H and has values in the range 0,1. Now, one important point is that you don't always need to hold out data. You can just reuse the validation data. So in some sense, depending on how sensitive your application is, how much data you have, and so on, you may either want to have a separate data set just for calibration because you really care about it, or you may not want to hold out additional data, in which case it still makes sense to run a recalibration step on your validation data, which is kind of free. You're already holding that out, and actually helps in terms of improving the calibration, even if you reuse the calibration, the validation data. So while I was practicing this talk yesterday, I had this question like, is my calibration data and training data and test data IID, or like what's happening? So I would say that as of now, I don't yet have any statistical assumptions at all. So it could be any kind of data, but if it helps, you can think of calibration and test data as IID, and that's what our theoretical results are going to be in, and that's what my experiments are also going to be in. So I'm not going to be going into covariate shift and other kinds of shifts. So you can think of your test data and your calibration data as IID. And importantly, your training data could be anything. So you could have picked up a model and say, trained a model in New York and calibrated it in Pittsburgh. But as long as you're testing in Pittsburgh, that's fine. Okay, so far we're still in the binary calibration setting. And here's where, like I mentioned, the focus of the talk is multi-class, which is the reason for that is that there's a bunch of literature on how to do binary well. And I'll quickly review that literature and give you an intuition of why binary is sort of not solved, but there's a bunch of ways to look at it, and why why it makes sense to leverage binary to solve multi-class. So the main problem, as I mentioned on the previous slide, is to transform G to H. And the intuition is that although G may not be calibrated, which means that these two things are not equal, it could be true that G is a very good classifier, which essentially means that there's some kind of monotonicity. It doesn't mean this, but you expect that there's monotonicity between the probability of y equals 1 given gx and gx. So even on that miscalibrated adult data set, you could see that there was a trend of increasing probabilities, but they were miscalibrated. So larger scores of G in some sense indicate larger probabilities of y equals 1. And the implication for our problem is that now you can just learn this simple wrapper M around G, which is a function that takes values from the output of G to the output of H. So just renames in numbers in the output of G to the output of H. So I have this example, which we'll go deeper into in the next slide. But basically on the x-axis, you have what G predicts, and on the y-axis, you have what H predicts. So whenever G said something like 0.8, the blue curve would say almost 0.9. So it's mapped 0.8 to 0.9, whereas the green and the red curves would say something a little less than 0.8. And that's the broad goal. So now we've reduced our problem to learning this mapping M. So we've reduced our binary post-hoc calibration problem to use some data to learn this mapping M. Okay. On this data, you have the GX values and you have the Y values, and you want to figure out what the remapping function is and how do you go to H. So the blue curve here is the popular method of flat scaling. So here, the transformation that's being considered is a linear transform in the logit space. So if you've seen the sigmoid function, then the logit is the inverse of the sigmoid function. Now, this is just some mapping that works well in practice. There's no reason for it to be the best mapping. So another proposal was made in which another parameter was added, and that was called beta calibration, and that's the red curve. So in each of these cases, basically the parameters A and B, as well as the parameters for beta calibration, would be learned on the calibration data. So you fixed G and you're just like kind of trying to learn a small set of 2 or 3 parameters with the explicit goal of being calibrated, while hopefully not sacrificing some important properties of the existing G. And that's why you don't want to completely change the model. You just want to change the output a little bit. Okay, another class of methods is non-parametric methods called binning. So these are essentially parametric methods. There are few parameters that you're learning, but you can have a non-parametric mapping. In this case, for example, you can divide the interval 0, 1 into a number of sub-intervals or bins and learn a single value of hx for every bin. So as you can see here, basically you have this step function kind of thing. So for instance, in this region between roughly 0.1 and 0.15, you're only always predicting about 0.2. So you have, so it's a constant mapping of a chunk of the interval in 0, 1 to a single value hx. And this is a non-parametric method. There are few assumptions, but at the end of the day, it may end up not being monotonic. So it's more flexible, but it needs more data and it could do funny things. So I'm actually going to be using a binning-based method in my experiments later, and I'll tell you a bit more about one method called histogram binning. So does this broad picture for binary calibration make sense? I'm going to be moving on to multiclass in the next slide. Okay, great. Okay, so now we have a pretty good idea of, okay, we have some idea of what, how post-hoc binary calibration works and what a notion for calibration in binary is. And now the question is, can we leverage this extensive literature to solve multiclass calibration? And we immediately hit a kind of bottleneck where we're not even sure if what is the right notion of multiclass calibration. So the first proposal would be that you have this vector valued predictor H, which takes values in the L dimensional space, which is 0, 1 to the L. So in particular, you can think of it as a probabilistic prediction over the L labels from 1 through L. And so these are non-negative scores that add up to 1. Okay, so it's the probability simplex in L dimensions. And a canonical or an immediate notion could be that you condition on the prediction, you condition on what hx gave you, and you ask if the probability of y equals 1 was the first component of hx, which is h1 of x, if the probability of y equals 2 was the second component, and so on. And you do this for every label. But this has some problems. So we'll go over some intuition for how canonical calibration works, which will also indicate some of the problems through an example. So suppose you have a patient who comes in with some flu-like symptoms and you want to figure out what diseases they could have. So maybe you want to give them a particular test for one of the flu-like diseases, but you don't want to give them all possible tests. Okay, so you use a machine learning model that takes as input these symptoms and gives you some probabilities. So if you have like a dry cough, maybe it's more likely that you have flu or something like that. Now the question is, do you want this entire vector to be calibrated? So that's what canonical calibration would say. Like you would say that this entire vector should be calibrated. Actually, just taking a step back, I would say, why do you want this to be calibrated in the first place? Well, this model suggests that this patient is very likely to have flu. And if you just give them a flu test and don't worry about any of the other diseases, you'll probably get a positive. That's what the model suggests, but only if it's calibrated. So you want to be sure that it's calibrated in some way before committing to a particular prediction. So what canonical calibration says is that conditioned on this entire vector, which is 0.9, 0.05, 0.1, 0.01, 0.01, 0.3, this entire vector, the probability of disease being flu is 0.9, and the probability of disease being COVID is 0.05, and so on. And this is true like up to the smallest probabilities like allergies. And you can imagine that you don't actually care about all of these probabilities. Like if suppose just this was true, that the disease is flu, then you're kind of happy enough already. And more formally, this is a kind of curse of dimensionality that you've hit. So because every possible component can take like roughly 100 values, maybe if the least count is 0.01, but the vector can actually take many, many more values. So now what do you do? And now we come to the first contribution of our paper, which is top label calibration, which asks if the probability of just the predicted class, which is flu in this case, is calibrated. So formally, if you define C as the classifier, in this case, you'll be which is flu. So what is the top class or the top label? And H as the confidence, which is the predicted score or probability for the top class, then this prediction would be calibrated if the probability of the disease being flu, given the prediction of flu and the score 0.9 is actually 0.9. Okay, so if something like this holds, then you're quite confident that you don't have to do a COVID test or allergy test. And more broadly, the notion of top label calibration in the language of conditional probabilities asks this to be true almost surely for all possible values of Cx and Hx. Okay, so let's look at that a little bit more. And the main idea is that now I've reduced multi-class calibration into this single binary calibration requirement just for the top label. And this is like a symbol, you're conditioning on scalars and you're asking if a single binary calibration claim is true. You no longer care if everything else is also calibrated. So what top label calibration is saying that when class L, little l was predicted with probability score R, is the observed number of times of frequency of y equals Cx also R. And if that is true, then you would be top label calibrated. So are there any questions about top label calibration?
Hi, Chirag. Can you hear me?
Yeah, Sid, go ahead.
Yeah, so to deal with this curse of dimensionality, what if you treat your multi-class classifier as n binary classifiers? So it's classifying flu versus not flu. It's also classifying COVID versus not COVID.
Mm-hmm.
And then,
yeah.
So how is this?
So
yeah, what do you think about this approach?
Just on the next slide, I'm going to be talking about another multi-class to binary reduction for calibration, which is exactly what you said. It's called class-wise calibration. So basically, we are saying that if you have a high accuracy or a high confidence setting where you're very confident about the top label, then you probably don't care about the others. And in that case, top label makes sense. But maybe some of your classes are very sensitive. And I'll give an example on the next slide. And you want it to be calibrated for that class, irrespective of what else is predicted. And in that case, you would go for class-wise. So overall, the message of like this talk is going to be that depending on your application, you should write down what binary calibration claims you care about, and then actually you can achieve them using a general purpose algorithm.
That makes sense. Thank you.
Okay, great. Thanks for that question. That's also a prelude to the next slide. But before that, I'll just mention this notion of confidence calibration, which is very widely popular in the ML literature. So if you've read anything on calibration recently in ML, you've probably come across this. And our notion of top label calibration looks very similar, but there's one fundamental difference in that confidence calibration just conditions on Hx and not the actual predicted class Cx. And that's like a serious interpretability issue because it's sort of philosophically inconsistent with the basic notion of conditioning on what you're reporting. So if I give you a disease prediction and a probability, well, I have to give you a disease prediction and a probability. I'm not just going to report a probability. So I won't go further deeper into this, but if some of you are very familiar with confidence calibration, we can chat offline about the differences between top label and confidence. And also you can check out the paper. Okay, so any ML predictor can be post-hoc top label calibrated, and how, what, in what sense, and how, and what are the guarantees? I'll come to that, but before that, we'll go to this question of what are the other notions of calibration, and why, and how do they compare to like top label calibration or canonical calibration? And the general strategy that has sort of come out in the ML literature is to reduce multi-class calibration to a number of simpler binary calibration requirements. And this corresponds to also like a one versus all thing, which Sid was mentioning a few minutes ago. And I'll illustrate that on this slide. So this is basically the notion of class-wise calibration. So recall that for canonical calibration, you're conditioning on the full vector hx, but instead you could say that, well, when I predicted h flu of x being 0.9, was that correct, irrespective of what else was happening around my vector? So I'm again conditioning on a scalar. And when I predicted h COVID to be 0.05, was that correct? So for example, we know that testing for allergies is much more intensive in terms of time and human effort and cost. So on always testing allergies is hard. So you want to be probably calibrated for allergies, irrespective of what happens in the other cases. Or maybe at the height of the COVID waves, you actually want to be very calibrated for COVID as well. Like even before doing the test, you want to be sure if you want to know if a person has COVID or not. And that's where we go to this notion of class-wise calibration. Now again, so just to illustrate the difference again, like instead of conditioning on this full vector and evaluating the full vector on the right, what I'm saying is that you could just evaluate the first element and it looks great. The second one, not so much. The third, it looks okay, but perhaps if you normalize by 0.01, then it's not so great. So you know, you can basically look at every possible binary calibration claim in a separate manner and get conclusions from that. Okay, so yeah, so the basic idea is that you've reduced multiclass to binary. So even though you have this new different notion of calibration, which is different from top level calibration, you're still reducing multiclass to binary calibration requirements, but there's more than one. Okay, and this broader framework or scheme actually applies to all popular notions of ML, of calibration that have been proposed recently. And this includes not just our notions, but existing notions, and also something called top K confidence calibration. So this Gupta is not me, and as far as I know, there is no relationship between him and me. But yeah, so but this is our notion. Okay, so now we're going to be moving on to how do you actually achieve these various notions of calibration. So, and that's calibration algorithms. So as previewed in the binary setting, any ML predictor can be post-hoc calibrated, and it can be done with respect to any M2B or multiclass to binary notion. And this notion like gives you a recipe for doing it almost. So in some sense, so the moment you've written down a bunch of binary claims, you can actually try to satisfy them separate one by one. So the overall recipe is that you carve out a number of binary data sets from the overall multi-class calibration data set. And this corresponds to one data set per claim. And now you use a binary calibrator to achieve calibration on each of these data sets. So I'll go into the details for top label calibration for this broader framework, but this broader framework applies to any M2B notion of calibration. So before that, let me quickly again review the post-hoc setup. You have this black box, which takes in a miscalibrated model. And now I have a bold-faced G. Could be any model which is learned on training data. And this training data may not even be IID as your calibration or test data. And now you have some additional calibration data. And you want to finally get a calibrated predictor on the right. And just recall again that you don't need necessarily to hold out the data. You could reuse validation data. Now for the, so on the previous slide, I was not clear about, what is this calibrated predictor? And that's deliberate because now it depends on what your M2B notion is. And depending if you have a particular M2B notion and you have 10 different binary calibration requirements, then we're going to output one calibrated predictor per requirement. So we're going to say that this is a probability if this is the requirement that you care about, and so on for 10 different requirements. Okay, and let's go into the top level calibrator in particular. So suppose, so in this case, instead of this vector valued G on the left, we actually just care about the classifier and the confidence predictor. So for simplicity, I'm going to assume that you've derived it from G. But in principle, you could actually just learn C and G. I don't know of ML predictors that do that, but in principle, that's all you need. Okay, and on the right, what we're going to do is we're going to recalibrate your confidence from G to H. And we're not going to change the classifier C, which means that our accuracy, like arguably one of the main things that you have, especially in a deep learning setting, which is very high, does not change at all. So you're going to recalibrate just the confidence, but without changing the accuracy. But in some sense, this is also a con possibly. Like it's possible that when you do this recalibration, you realize that, oh, I should have actually been classifying something else. But in a high accuracy setting, that's probably not going to happen. It's probably likely that you were just saying 99% when you should have been saying 95%. So the labels are now going to change, and that's what we're going to have for our algorithm as well. So let's get into this algorithm, and what we're going to do is use binary calibrators at the core. So we're going to carve out a number of binary calibration data sets, and then we're going to use a binary calibrator in the end. So as on the previous slide, you have a top label predictor and a confidence predictor and calibration data. Now for each class L, you create a separate data set, which we call DL. Now this looks like a one versus all data set, but very importantly, because you're conditioning on the class, we want to separate out each of the classes into different data sets. So here I have this conditioning on CXI equals L, which means that I pick up all the calibration points for which the class little l was predicted, and only those points appear in this dataset DL. So all of the features Xi's are kind of independent across these classes, depending on which was the top label predicted for that class. And here is where it's like fundamentally different from one versus all, where for each of the L classes, all the points would appear in all of these L datasets. And finally, you replace the label Y with an indicator of whether it equals the particular class or not. So this is similar to one versus all. So just to illustrate this on a very simple case, suppose this is your big data set, and focus on these first 2 points. You have x1, 2 and x2, 1. And suppose you predicted the class 1 for these 2 points and some other class for all of the remaining points. So now D1 would basically take these 2 points and you just have these 2 points in D1. And you're going to replace 2 with indicator of 2 equals 1, which is 0, and replace 1 with indicator of 1 equals 1, which is 1. So basically, in this case, the class prediction was correct, so I get a 1. In this case, it was wrong, so I get a 0. And now I consider recalibrating G. So if I was very confident about the class 1 on this point, then I probably have to change something. And if I was underconfident about the class, about the probability of the class being 1, I may have to change something. So of course, this is just 2 examples, but in practice, you'll have hundreds or thousands of examples per class. Okay, and so now you're going to learn for a different calibrated predictor HL for every class. And this is going to be given by your favorite binary calibrator. This could be any binary calibrator that you like. You put in DL and you put in G and you get HL out of outside. Okay, and finally, I'm going to be merging this to form a single edge. So remember, I said that at the end of the day, you get a single edge. And the merging step is very simple. So so remember that I'm not changing the classifier. So when I get a point, little x, a test point little x, I take its class and and the confidence I predict is the confidence that that predicted class, the h corresponding to that predicted class gives. So it's you just write it succinctly as HCX of x. Okay, so does this algorithm make sense? In the next slide, I'll go into what this binary calibrator is. Or as I said, you can use any favorite binary calibrator. I'll talk about what my favorite binary calibrator is. And and then put it all together. Okay, looks like everything makes sense. So the binary calibrator that I will be using for the experiments and for the theory is histogram binning. So as I mentioned earlier, I've studied, I have a couple of papers on binary calibration, and in those works, we've kind of found out that histogram binning has a bunch of nice properties, and it actually performs well in practice and in theory. So I'll give you a very quick intuition of what this is doing. We won't be going too much into too many details. So suppose the dots here are your calibration points. Okay, what I mean, they're not the features, but they're the GX values. So remember that I've conditioned on G, and now all I care about is remapping GX to HX. So in some sense, my entire feature vector X is simply represented by the single GX value in this interval 0, 1, and those are the dots. Now using the calibration data, which is these GX values, I'm going to divide this interval 0, 1 into a number of bins. Okay, so in this case, suppose you have 4 bins. I divide them into these 4 bins, which means that I learn these boundaries on the calibration data. So these bars are the boundaries. And I'm trying to do that so that each of the bins have roughly the same number of points. So there could be parts of the interval which are highly which occur much more commonly, and parts which don't. So hence I'm not going to consider a uniform division of 0, 1, but a division that's adaptive to the number of points that occurs in the interval 0, 1. And now I'm going to use the Y values to estimate the probabilities in each of these bins. So I don't have that on this slide, but you can imagine that each of these points have a corresponding label, and I use those to estimate the probabilities. Now, when a test point little x goes to the bin 3, then I will predict hx equals p3. Okay, so suppose like these are roughly 10 points, maybe 7 out of 10. So it's closer to 1. So you expect that the probability of y equals 1 is high. And so maybe 7 out of 10 were 1 on the calibration data. Then I'll predict 0.7 for hx as well. So as I mentioned earlier, for binning methods, you have these kind of step function kind of things. So you're not making you at the end of the day, H just makes 4 different predictions, but it's guaranteed to be calibrated. So what do I mean by that? I'll come to the guarantees in a second, but basically this method was proposed by Zadrozny and Elkin in a popular paper in 2001. And just recently, we showed that it's actually distribution-free calibrated for binary classification. And in another paper, we'd also shown that some kind of binning is necessary for distribution-free calibration. So in some sense, histogram binning is almost necessary and sufficient if you care about calibration without any distributional assumptions on your data. Okay, so I won't be going into the binary calibration guarantees, but we'll go into how what the final guarantee looks for top label calibration. So I'll be proving I'll be showing the result for distribution-free top label calibration. So this slide and the next are slightly heavier on the theory and the math, but then right after that, we'll move on to the experiments. So the setup is you have given a model, miscalibrated model CG and some calibration data D, and you want to learn a top level calibrated function H. So you want to go from G to H. The assumption, as I mentioned earlier, is that your calibration data D and test point are IID. So this is crucial to our result and also like the way we think about this work. So if you have significant distribution shifts between what you're using for calibration and testing, then you would have to do some kind of corrections. And I'll briefly mention what corrections are possible later, but you're not going to, like, this talk is under the assumption that everything is IID. But when I say distribution free, I mean that I make no assumptions at all about what this distribution is. It could be an arbitrarily bad distribution, and I make no assumptions at all about it, but it has to be IID. So it could be a very, very bad, it could be a bad distribution, basically. And the result holds for any distribution. And the informal goal is the top label calibration, where you want approximately these two things to be equal. Okay, and to define that formally, I'm going to call the left thing an LHS and the right thing an RHS. So formally, if you have some level of approximation or like tolerance between the difference between LHS and RHS, and some probability of failure alpha, which is something small like 0.1 or something like that. And you have this, now this algorithm A, which takes CGD and gives you H, is distribution free top level calibrated. If for any data generating distribution, with high probability, so with probability 1 mass alpha, the LHS and the RHS are epsilon close. So it's kind of like a pack style guarantee, but there's one important a subtlety that you're actually having the probability also over the calibration data. So I'm not, so it's marginal over the calibration and the test data. This is like subtlety which we won't go into the details in this talk, but if you're more interested in the theory, we can talk offline. We have two more kinds of guarantees, and the main one that I'm going to be presenting on the next slide is this one, which is most simplest to understand. It's just that the expected value of the difference is at most epsilon. Okay, and that's the main guarantee that I'm going to be showing. And finally, you could also have a conditional calibration guarantee, which is much stronger than both of these. It's saying that for every possible value that H and C could take, so every label and every score, you simultaneously want calibration. Okay, and this is much stronger, and it probably is in some kind of sensitive setting where for every patient you want calibration or something like that. But the top label histogram binning method actually achieves all three of these guarantees. So I'll present the ECE guarantee, which is, if you recall, the expected value of the difference between the LHS and the RHS. So now if you fix the number of points per bin, this is the only hyperparameter of the algorithm. You fix the number of points per bin, which is K, let's say it's 50. Then for any P, the expected ECE, so it's kind of like an expectation of an expectation, which is weird, but you need that for making it formal. The expected ECE, on average, you'll see that the ECE is at most square root 1 over 2K, which is 0.1. So I do say informal here, but this constant is tight. So we actually get a guarantee which is meaningful. Like at the end of the day, I won't say that the difference is at most 1, which is trivial or something like that. Like this, just for 50 bins per points per bin, you can actually get a very meaningful guarantee. And in one of my papers, I actually show that it's tight in many settings. Like you actually empirically see this behavior as well. So you will notice that there's no labels or number of labels that appears here. So it looks like a kind of free lunch. Like even if you have thousands of labels, you still get great calibration. And that's not true because so what is kind of being hidden by this clean guarantee is that if the number of bins are proportional to L, which is what you would want, if you have lots of labels, you want different bins for every label, and you want like a bunch of predictions, then the number of points per bin kind of scales down. And you'll end up getting like a square root L factor here if you fix this parameter. Okay, so this is the end of the theory part of the talk. We'll go on to some experiments, but if you are more interested in this, we can talk more, and you can also go to the paper and see that we can show similar results for all M2B calibrators and specifically for class-wise histogram binning as well. Okay, so let's move on to the experiments. So the setup is as follows. You have now this G is a miscalibrated deep net model, which tends to be overconfident usually. And we're going to be using the validation data as the calibration data, as I suggested is possible. And especially in deep learning, and for the standard data sets that we're going to be looking at, people probably don't want to hold out additional data. You want to see what you can do with the existing validation data. And you may ask that, oh, validation data is no longer IID with the test data, even if it was earlier, because you've used it for hyperparameter tuning and early stopping and all of that. And that's completely true. But it turns out that it's still somewhat pristine. Like it doesn't lose all of its IID-ness with the test data. And it's still much better than recalibrating on the training data itself. So it's still useful to use the validation data again. So the data sets we'll be looking at are popular vision data sets called CIFAR-10 and CIFAR-100. So here 10 and 100 refers to the number of classes. And these are like simple classes like car and a man and a truck and things like that. So CIFAR-10 has 10 and CIFAR-100 has 100. And very importantly, to get an idea of what is the scale we are working with, we have 5,000 validation points. So you also have a number of training points, but remember that we don't actually care about that part. And you have a number of test points, which is eventually used for assessing how our model is doing. But the main heavy lifting or the main statistical like this, the overall statistical problem is over these 5,000 validation points. Okay, so that's the number of points that we use. And you can already probably think that CIFAR-10 with 10 labels is relatively easier than CIFAR-100, and we'll come to that. That's actually true. The metric that we'll use to compare is an estimate of the ECE on test data. And we'll have different notions of ECE corresponding to the appropriate M2B notion of calibration. And finally, we'll compare to these popular methods called temperature scaling, vector scaling, and directly scaling. So if you've seen any literature on calibration, you've definitely come across one of these methods. And these are very popular. These are parametric methods that we'll be comparing to. Okay, so I have like a big table in the paper, but in this talk, I won't bore you with like that big table. We'll go into just some specific case studies on specific data sets and specific notions of calibration. So the first is top label histogram binning. And we compare it to this very popular method of temperature scaling on CIFAR-10. And we vary the number of bins. So like I mentioned, this number of bins ends up being a hyperparameter. And it's important to see what happens as you vary it. And also for ECE estimation, you need some kind of binning. And there are papers which have argued that depending on the binning scheme, one method could be better than the other. But here you see that the solid green line, which is the top label ECE of histogram binning, is always below the solid orange and blue line. So the orange line is temperature scaling and the blue line is the base model, and the sort of miscalibrated model. So as you can see, the model is not terrible in the first place, but both temperature scaling and histogram binning improve it, and histogram binning is consistently better. I also have these dashed lines, which is the conf ECEs, the confidence ECEs. But in this paper, we are arguing for replacing top label with confidence. So we're not going to be talking about these dashed lines a lot. So we have similar results. So this was on ResNet 110. So the pre-trained model was ResNet 110, but we have a bunch of results on other models as well. And just a quick note on the scale of the ECE. So these errors are like maybe about between 1 and 2%. So it's a very small scale, but at that, in deep learning, like at that kind of where everything is 95% or 90% accuracy, that 1 or 2% is actually very meaningful. Another notion that we do really well for is what is called the maximum calibration error. And this is related to the conditional calibration guarantee, where you're looking at the worst possible difference between the LHS and the RHS. Okay, and here you see that histogram binning does much better. So I'm looking across bins and across labels, and I'm saying, what is the worst calibration that you ever had? And it turns out that temperature scaling and the base model almost do as bad as a trivial predictor. So they're almost at the 0.5 level, which is what you would get if you always just predicted 0.5. Whereas histogram binning goes all the way down to almost 0.05. So in some sense, for across all predictions, you're never more than 10% or 0.1 miscalibrated. And just for comparison, I have this ECE plot from the previous slide, which is at a completely different scale. Finally, we have similar results for a bunch of other architectures as well. Finally, a thing I previewed briefly earlier was that we expect histogram binning to do worse on CIFAR-10, CIFAR-100 because of the number of classes being higher. And I have some intuition here about the fact that top label calibration kind of splits the classes across different data sets. I won't go into the details, but basically you perform this data set splitting operation, and now you're splitting it into 100 different data sets. So you're losing a lot of statistical efficiency. And you actually see that in practice as well. So we observe that the EC performance dips So the top label EC performance dips. So the green curve is actually much worse, but the maximum calibration error is still comparable. So if you care about like being conditionally calibrated for every prediction, then even if you have a very hard problem, histogram binning tends to do well. Finally, we have results with class-wise calibration. And because we didn't go too deep into class-wise histogram binning, I won't spend too much time on this. But basically, for CIFAR-10 and CIFAR-100 across architectures, class-wise calibration class-wise histogram binning just does better than every other method. And all of this is actually based on a simple suggestion based on our theory, which we say is that do not normalize the output of your class-wise calibrators. Treat them as L different calibrators. Don't normalize in the end. And the red curve here is the normalized version, and that's just way higher than everything else. So finally, I have like a note for practitioners. So a lot of this talk was, if you're in the ML community, you're using calibration for like a broad problem. But what if I have a specific problem, and like I don't know, do you care about calibration? Well, if you're using probability scores, you probably do care about calibration, or you could benefit from calibrated scores. And now maybe you're not sure what your problem, what is the right notion of calibration. So I would suggest that based on our work, you first write down a bunch of binary calibration requirements that fall from your application. And now you can achieve each of these based on our framework. Okay, so this is like a short takeaway for a practitioner. Finally, IID is a modeling assumption. We know that data is never IID, but sometimes it's a decent assumption. But maybe for your data, it's not a great assumption. So if that's the case, there are ways to work around it. There's some work in my lab, but there's some other work, and there's also future work that we're working on. So if you're very curious about it and you want to apply calibration, but you have highly shifted data or adversarial data, then we can talk more about that offline. I'll leave you with this slide, and you should check out my repository if you're interested in applying this to your problem. And we already have code for top label calibration, and I'm going to be putting more code for class-wise and other M2B notions of calibration as well. So thanks a lot.